AP Calculus BC, Unit 9, Day 3 lesson. Warm up first. So on the warm up, does the series converge or diverge? Justify by naming and demonstrating the convergence test. And I want you to use as many tests as you can come up with, just to see if you recognize which ones are applicable, just in case one doesn't work. This will be helpful in the future. So pause the video and try these problems. Okay, assuming you tried these. Now, this first one, I don't know if it sticks out to you, but this is a geometric series, and you could write it in a way that's a little more obvious. But this has an r value to an n power, so this is we could say, well, the absolute value of r equals the absolute value negative 3/4 equals 3/4, which is less than 1. So it converges by the geometric series test. You could also find the sum, which is something I'll probably have you do on your next test. You could find the sum and be a over 1 minus r. The a value is 1. R value is negative 3/4. It's 1 over 7/4, so it is 4/7. So that's the sum. This is the only kind of series that we find, that I ask you to find the sum of, is geometric series. Okay, but we could also try the nth term test, which is the limit as n goes to infinity of this. Now, this will go to 0 because you're multiplying by a fraction, but that is inconclusive. Okay, and ratio test, which is the limit as n goes to infinity, the absolute value of negative 3 to the n plus 1 over 4 to the n plus 1 times 4 to the n over 3 to the n. Rules of exponents gives you the limit. I haven't even tried to take the limit yet. And I have this, which is 3/4, which is less than 1, which converges by the ratio test. Okay, next one is not a geometric series, so we cannot do that. So we could try the nth term test first. And that'd be the limit as n goes to infinity of n plus 5 over 2n minus 1, which these are the dominant terms. It's going to go to 1/2, which doesn't equal 0, which is conclusive. It diverges. So we could try the ratio test and see what it does. So limit as n goes to infinity of, and so now I'm just wanting to see if I can pull it off the other way. So it's going to be n plus 6 over 2n plus 1, because the n plus 1 gets multiplied by the 2, times 2n minus 1 over n plus 5. And this is going to go to 1, which is inconclusive. So it's interesting that usually the nth term test is inconclusive, but here the ratio test was inconclusive. All right, next one, we're trying to find the radius of convergence. So we go directly to the ratio test for power series. This is a power series. It has x's in it. Those other ones were number series. Limit as n goes to infinity, absolute value of 4x minus 5 to the 2n plus 3 over n plus 1 to the 3/2 times n to 3/2 over 4x minus 5 to the 2n plus 1. Now let's use rules of exponents to help us out here. That's going to leave us squared. So we can rewrite it limit as n goes to infinity of the absolute value of, we could put the n over n plus 1 together all to 3/2 power. And then we have a 4x minus 5 squared. Now, this is going to go to 1. And so we get absolute value of 4x minus 5 squared has to be less than 1. So now we need to solve this. Now, if this squared is less than 1, then that also means the absolute value of 4x minus 5 is going to be less than 1. Right? So if you want to find the radius, you could divide both sides by 4 right now. And you get absolute value of x minus 5/4, which is the center, is less than 1/4. So there's your radius, and your center is at positive 5/4. Or you could go ahead and start solving it. Negative 1, 4x minus 5. Probably add 5 to both sides first. So we get 4. Divide both sides by 4, or all three sides by 4. So the diameter is from 1 to 1.5 is 1/2. So the radius has to be half of that. The radius is 1/4. So, there you go. Okay, let's talk about some other series, special kinds of series, special kinds of tests. So there's something called the harmonic series, which I brought up a few times. And if you were to write it out from closed form to open form, would be 1/1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... If the terms are getting smaller. If you were to do the ratio, or the you could do the nth term test, you could do the ratio test. So nth term test, let's try that real quick. Limit as n goes to infinity of 1/n equals 0, which is good, but it is inconclusive. So it's not really good, it's not really bad. So the ratio test is going to be the limit as n goes to infinity of the absolute value of 1/n plus 1 times n, which is going to be 1, which is also inconclusive. So still don't know. Okay. But I'm just going to let you know it diverges. Okay. We'll get to how we'll prove it soon. Now here's another series that looks just like it. This is not a harmonic series. But it has a little extra squared here. So it looks very close to this, but this has a power 1, this has a squared. If you look at the terms, 1/1, 1/4, 1/9, 1/16. Terms are getting smaller, right? If we were to do the nth term test, limit as n goes to infinity of 1/n squared, it would also give you 0, which is inconclusive. Okay, and then we could try the ratio test. One over n plus 1 squared times n squared, and it's going to equal 1 also, which is inconclusive. So very similar to the other one. I mean, it looks very close. This one, I'm going to cut to the chase. I'm going to prove to you, converges. I mean, they're so similar. They're so like each other in so many ways, but one blows up and one doesn't. So we're going to research, we're going to come up with another test that we can apply to this. So this is a new test called the integral test. And it says let this right here, this is a sequence, okay? They need to be positive, okay? And suppose that any single term in that sequence equals some function. So the terms in a sequence usually have a pattern, and you could probably create a formula that would give you any single one of them. So that's what this is. It's got to be this function that we use to find these discrete terms in sequence, because terms in sequence don't have all the values in between them. But this function, you can plug decimals in and stuff. So it's positive, it's continuous, and it's decreasing. It's got to be getting smaller. Okay, if it's not decreasing, if the terms aren't getting smaller, then you have no shot. So now, so we have a series, and then we also have another function that we integrate. Series are accumulation. They are adding them all up. Integrals are also adding. And this says that they're both going to converge or they're both going to diverge. So this series, adding up all its discrete terms, and this function, if you integrate the area underneath it, and it converges, it's going to go to, it's an improper integral. So we studied these at the end of last semester. So now we're seeing a great application of them. If this converges, that converges. If this converges, that converges. If they either both converge or they both diverge. Now we're not saying that they equal each other. They definitely don't equal each other, but they both have this same behavior. So here's a way to help kind of, prove to you how it works, okay? So let's take this series up here. This is the harmonic series, right? So we're going to use the harmonic series. Now, harmonic series, the terms are 1 over 1 plus 1 over 2 plus 1 over 3, and on and on and on. So if what we could do is we could represent these as the area of a rectangle. So, generally, we're not thinking of these as area, but we say, okay, well, here's one, that's the area of 1. And the next one's going to be the area of 1/2. And the next one's going to be the area of 1/3, and so on. Okay, because these terms are just individual numbers. So I'm trying to kind of make them look more like the area under a curve. Okay, now, if I were to compare this to the integral of, and this n is just for some value, okay, some starting value. So if I were to compare these areas, would you guys agree that this is the upper bound for the integral 1 to infinity of 1 over x dx? So here's the function 1 over x, right? And we're plugging in these discrete values. Those numbers are the values in the series. But if we integrate it, see how these values are an upper bound. I kind of want to also say overestimate. It's an overestimate for it, right? So this is kind of like the Riemann sums, which sometimes will be more or less than the actual curve. So these are more than the area under the curve if we take this to infinity, right? If we take this to infinity, that if you add up all these rectangles, it's going to be more than the integral underneath, okay? But here, we're going to do something fancy. We're going to shift this whole series left. If we shift the whole series left, then we get all the same rectangles, but we're starting at 0 now, and it's an underestimate. If we shift it left, we get a lower bound, an underestimate for the integral 0 to infinity of 1 over x dx, right? You get a lower bound, an underestimate. Okay, so this is kind of tricky. So that means that we can shift this and compare it to a function that starts at 0 instead, and then it actually does fit underneath it. So these functions are going to behave like each other. So 1 to infinity of 1 over x dx. Now, we're going to actually go ahead and integrate this and see what happens to this area under the curve. Okay, so we're comparing these two things. Comparing this function, trying to make a visual representation of it, and this improper integral. Okay? I'm trying to compare them to each other. So what we've kind of shown right here, what we've tried to show, what we have shown, what we're trying to show and communicate is that the area of all these terms, if we represent them with the area, it's either an overestimate for this or an underestimate for this, okay? So whatever happens here, they should kind of work together. So if we were to go ahead and integrate this, integer would be natural log the absolute value of x, and we're going to go 1 to infinity. We're taking the lazy approach instead of writing the limit as b goes to infinity with the b and all that stuff. Limit of infinity minus natural log of 1. This is going to be 0. Natural log of infinity blows up. It goes to infinity. It diverges. And so because this related improper integral diverges, then the series that goes with it also diverges by the integral test. So we call this the integral test, okay? So we've shown right here that harmonic series up there diverges by this integral test. Let's see if we can apply. So this is, nth term test is your first bet. Ratio test is probably your next one. If both of those don't work, then you might want to use this test, the integral test. And for now, you might want to practice all of them, but on a test, you only want to use one. So let's see if we can do this one. This is the same thing as x to the negative 2. So that's going to be x to the negative 1 over negative 1, which is going to be negative 1 over x, which is going to be negative 1 over infinity minus negative 1 over 1. That goes to 0. This goes to 1. Okay, now the takeaway here is that it converges. Okay, the value is not actually important. Because this one converged, then the series n equals 1 to infinity of 1 over n squared also converges by the integral test. Now, I want to make sure you understand that the series 1 over n squared does not necessarily equal what that one equaled, okay? They just both behave the same in converging or diverging, okay? All right, now let's add another test. That's sort of a special case of what we've been just looking at. And so the integral test, sometimes we use tests to create more specific tests that work just for certain functions because it's quicker. So it's got something called the p-series test. And p-series is whenever you have 1 over n to a power. You think of p as power, like power test. P-series test. So any series that has this form, we call a p-series. And we're going to see there's certain values of p that converge and certain values of p that diverge. So we could just try this out real quick and see what happens. Like let's, if p series of p equals 3, that would be the same thing as 1 over n to the third. And so let's see if we can figure this out using nth term test is being inconclusive, ratio test is being inconclusive. So then we would resort to the integral test. Now, watch, the n becomes an x here. So this is all for number series, but then when we compare them to a regular function, we got to put x's in there. So it's going to be x to negative 3, so it's going to be x to negative 2 divided by the new exponent. So we rewrite it, negative 1 over 2x squared. Negative 1 over infinity minus negative 1 over 2. So this goes to 1/2. So it converges. So that p-series converges. So p equals 3 converges. How about p equals negative 2? Well, let's try it out. Let's see what happens. Now, it's going to be n to the negative 2. So it's always, the n is always to the p, the power in the denominator already. And so what this becomes is this becomes n equals 1 to infinity of n squared. And we can actually just prove by the nth term test that that the limit as n goes to infinity of n squared is going to go to infinity, which is not equal to 0, which diverges. So it diverges. This one for sure just blows up. We could use the integral test. I mean, this would not be a great place to use it if you didn't have to. It's just good practice, though. And says, okay, well, one, they're already going to tell you that you really shouldn't use the integral test because the terms are getting bigger. It's increasing. You can use it. It's just kind of pointless, I guess, because the nth term test is so much easier to use. So we could try this out. Integer is going to be x cubed over 3. You can go 1 to infinity, and you're going to get infinity minus 1/3 is infinity, and so it diverges by the integral test. Now, I'm just trying some different possible p-values out. So p equals -2, diverges. P equals 3, converges. P equals 1. Well, that's the same as a harmonic series. So by the way, a harmonic series is a p-series with an n value of 1. And we just showed that the nth term test and the ratio test are inconclusive. So then we use the integral test. We already showed this on the front. Get natural log, the absolute value of x. So we get natural log of infinity minus natural log of 1, which is 0, and it blows up. It diverges by the integral test. So p equals 1 diverges. Now, I'm just going to go ahead and cut to the chase. What happens, so harmonic series p equals 1 diverges very slowly. Like it doesn't blow up right away. It's so close to converging that if we just nudge the p-value up a little bit, it would converge. Okay? So it goes to infinity. It takes e to the 19th terms to reach 178 million, which isn't that big. Okay? That many terms just to get to the partial sum of 20. So even after almost 200 million terms, it's still just at like 20. All of them added up. All those first 200 million terms added up are still like 20. Okay, so it's diverging. It's going to infinity very slowly. Okay, but it does. It continues to get bigger. So it's really slow. So here's the conclusion for a p-series, and we're going to use this now in the future. P-series test. If it is a p-series and p is greater than 1, then it converges. If it diverges, if p is less than or equal to 1. So this is quick. If you're like, hey, that's a p-series and p equals 2, and that's greater than 1, it converges. Done. And then you don't have to do the whole integral test. So if it's p-series, we call it the p-series test. Now we figured it out from the integral test. Now what about an alternating? So a harmonic series always diverges. And that's another conclusion that you can just write. Hey, it's a harmonic series, it diverges. Or if you're doing a comparison test or something like that. Now an alternating harmonic series, that's a little different story. Okay, I've said before that alternating series will converge quicker than their absolute, counterparts. And so the harmonic series, the partial sum's 1, then it's 1/2, then it's 1/3, and then it's 1/4. And what happens is it blows up. It goes to infinity. It never reaches a wall. It never approaches a wall. Okay, so this is a harmonic, right? But an alternating harmonic has the same terms, same numbers, but it's going plus, minus, plus, minus. It's changing signs, okay? And what that looks like is 0 to 1. So the first partial sum is here at 1. The next partial sum, you subtract 1/2, and it goes to here. The next partial sum, we add 1/3. So what is that, 5/6? That'd be like over here, 5/6. And then the next term, you subtract 1/4, And so, I mean, it's going to get hard to, I'm not going to bother to write all these, but if we subtract 1/4 from this, that would be 20 24ths minus 6 would be 14 24, 7/12, 7/12. So it's definitely, it's bigger than 1/2. 7/12 would be the next one. And so what happens is we go back and forth, back and forth, back and forth. And you can see, even just with the first partial sums, that it's converging to some value. So this is just a visual version of it. But the alternating harmonic series converges. Okay. So the way we write it right here, n equals 1 to infinity, -1 to the n plus 1, it's almost the harmonic. It has this extra -1 to the n plus 1 power on top, and it converges. Okay? Now, if you take the absolute value of it, you get the regular harmonic because it forces all the negatives to become positive, and it diverges. So it doesn't converge absolutely. Okay, and that's another term we've started putting out there: converging, absolute convergence. So it doesn't converge absolutely. It does converge though. Okay, so that brings up a new test, the alternating series test. So alternating series are special, and they are more likely to converge. Okay, and the alternating series test says if you have an alternating series, some kind of plus minus going back and forth every time, and the terms are positive, okay, will converge if the limit of the terms goes to 0. So this is like the nth term test. Like the nth term test. It is not the nth term test because it requires that it's alternating, but it's like it. So if it's an alternating series and the terms go to 0, that is enough to say it converges, okay? Alternating harmonic series is not absolutely convergent. So that's what is shown over here. Okay, it is conditional. We call it conditionally convergent, meaning it only converges as its original self. But if you force it to be all absolute, all positive, it will not converge. So we say it converges conditionally. Now, just to throw one more thing, this has been a really good lesson, lots of good stuff in it. Just throw one more thing in here. There is a truncation error. Remember Lagrange? I want to say Lagrange error bound. That way of estimating the error. There's a special way of estimating the truncation error of alternating series, and I'm sure you'll be happy to know that it is much simpler. Okay, so alternating series keep overshooting their limit, going back and forth, right? The truncation error for the nth partial sum is always going to be less than the next term. Okay, so if you look at what we were doing up there, the first one was 1/2, right? Well, the first partial sum was 1, and so here let me kind of rewrite this picture right here. Okay. So it keeps going back and forth, right? Now, if we just take the first one, then this right here represents the error. It's over what we're eventually going to converge to in the end. Now, here's the thing I can say for sure is that is less than the next term. The next term was 1/2, right? -1/2, which brought you to here. And this error was for sure less than that, right? And then the next term was 1/3, and that brought us back to here, right? And this, if we take this one, this error right here is for sure less than the next term. So what is the error here's just an example for the first 4 non-zero terms of an alternating harmonic series. Now we're only going to talk about error for series that even converge. Okay, so here's the hypothetical. So first 4 non-zero. So the first term was 1 minus 1/2 plus 1/3 minus 1/4. So that's the first 4 non-zero terms. So we're going to take that to estimate a series. Okay. The error, well, it's the next one. So this is where we truncate it. This is called truncating, right? We cut it off. The error is for sure less than 1/5. It's less than just the next term after the one you took. So much simpler than the Lagrange error bound, but it only applies to alternating series. Let me check. Okay, and just okay, it's less than this next term, and it has the same sign as that term. So the actual error, the error could be positive or negative. We usually like to think of it in terms of just being absolute value. But this fourth term here, okay, let's just start with the simpler one. So the first one is 1. Its error is an overestimate. So I guess we'd say it's negative is what they're trying to say. It's 1/2. It's less than 1/2, and it's negative. I'm not sure if I get that, and that's sort of like how it's supposed to be. Has the same sign as the first unused term. So it should have the same sign as that term. Okay. So in this case, it's a positive error of less than 1/5. Even though here it seems like it's a positive error, even though the next term is negative. So I don't know. I'm a little iffy on that. I'll have to think about that more. But usually we think of error as the absolute value of the difference between the actual value and the estimated value. So the sign of it, I don't think is usually something that we usually are concerned with. But there you go. Try the worksheets. Try all the possible tests that you can on any problem. If it's not alternating series, you can't use the alternating series test. If it's not a p-series, you can't use the p-series test. There, and so forth.